Hey guys, in this video, I will now introduce you to the last major topic of the course called series. Let us start by recalling what we have discussed during our last meeting. In our last meeting, we defined what we call a sequence, which is just a list of ordered numbers. We can also think of sequences as functions whose domain is the set of natural numbers. We also defined what we call convergent and divergent sequences. As a function, we can talk about limits. So we can talk about limits of sequences, particularly if a given sequence has a limit as n approaches infinity, then we say that the sequence is convergent. Otherwise, we say that the sequence is divergent. Now, in many applications, the sum of the sequences are also important. So in here, we will discuss the sum, which we actually call the series. So, an infinite series, or simply a series, it is an expression of the form sum of an running from n equals 1 up to infinity. So it's just the sum. Basically, it's just a1 plus a2 plus a3 plus etc. plus an plus 1 plus so on and so forth. The numbers a1, a2, a3, and so on and so forth, we call them the terms of the series. So a natural question that can be asked is that given an infinite series, does it have a sum? So do all series have sums? Or if the sum exists, how can we find them? So let us consider the following. We want to consider the sum n running from 1 up to infinity. So if this is our sum, this is just 1 plus 2 plus 3 plus 4 plus 5 and so on and so forth. So clearly, if you increase n, this sum will just increase, and therefore, this will just go to positive infinity. So this answers that not all series can have a sum. So the question is, do some series have a sum? Let us consider this series. We have 1 half plus 1 fourth plus 1 eighth plus 1 over 16 plus so on and so forth. Plus, in general, these terms here can be written as 1 over 2 to the n. So we just have 1 half plus 1 fourth plus so on and so forth plus 1 over 2 to the n plus the next term is 1 over 2 to the n plus 1 plus so on and so forth. What we're gonna do is to consider the sum of the first n terms. For example, let us consider the sum of the first two terms, 1 half plus 1 fourth, and we can easily get 0.75. If we consider the sum of the first three terms, we will get 0.875. The sum of first four terms, we get 0.9375, and so on and so forth. So in here, we have the sum of the first six terms, and the sum that we have obtained is 0.984375. And the next one, if we add 1 over 128, the sum will become 0.9921875. So let us analyze this quickly. If we consider these first two sums here, notice that the difference from the first sum here going to this sum here is roughly 0.125. And then from this sum going to this sum, notice that the difference becomes smaller. It's roughly 0.06 something. And then from this sum going to this sum, it became to roughly 0.03. And then this one here up to this, it became 0.016 something. And then from this point up to this point, it became, the difference is 0.008 something. So the point I want to make is that from this sum going to this sum going to this sum, for the two consecutive sums that we see here, it seems that the difference between the two sums becomes smaller and smaller. So if we added another term here, the difference from this sum to the next sum will become much smaller than the difference between this sum and this sum. So it seems that if we continue adding terms in here, it seems that the sum goes to 1. Okay? We will see later that the actual sum of this infinite series here is actually equal to 1. So, if you notice, what we actually did here is to consider the sum of the first few n terms. And how will that relate to the to finding the actual sum of a given series if the sum exists? This is actually a technique that we will learn, and hence we will use to define when the series has a sum. So, when does a series have a sum? Let Sk denote the sum of the first k terms of the series, sum an from 1 up to plus infinity. So this means that our S1 is simply A1, our S2 will be A1 plus A2, we continue, S3 will be A1 plus A2 plus A3, and so on and so forth. So Sk will be equal to A1 plus A2 plus A3 until plus A sub k. Or, compactly, we can write it as sum of n running from 1 up to k. This S's here, S1, S2, S3, and so on and so forth, we call them the kth partial sum. So Sk will be called the kth partial sum of this series here. And of course, if you collect these numbers, S1, S2, S3, and so on and so forth, the collection is a sequence itself. And we call it the sequence of partial sums. So, if it is a sequence, then we can talk about limits of this sequence, or the limits of the partial sums. If the limit exists, then this sequence will be convergent. If the limit does not exist, then this sequence will be divergent. But how will they relate to the series? So we define the following. Let sum of an be a series and denote by Sk its sequence of partial sum. If Sk converges to S, then the series is said to be convergent, and the sum of the series will be equal to S. Now, if this sequence does not converge, then we say that the series does not converge or is said to be divergent. Now, why is it that the real number where this sequence converges to is equal to the sum of the series? Well, just recall that your S sub k is the sum of the first k terms of the series. And when we talk about limit of sequences, we take the subscript to go to infinity. So in here, you will have the limit of sk, and we said that this is equal to s if it exists. But this one here means that you will have the limit as k approaches plus infinity of a1 plus a2 plus etc. plus ak, but you let your k approach infinity, so this will be equal to a1 plus a2 plus etc. plus ak plus ak plus 1 plus etc. and so on and so forth. But this one is exactly your summation of an, 1 to infinity. And just for clarification, I'll use a different subscript for this one since we are using the k here as the variable for our limiting process. So in here, I'll just use n plus 1, and here, and so on and so forth, which is, again, like what I said, is this series here. So yeah, if this sequence of partial sums converges to S, some real number, then this S is the actual sum of the series. So, in other words, this series here is convergent if the sequence of partial sums is convergent. And if you look at this sum here, an infinite sum, we can write it as the limit as k approaches infinity of this finite sum. I mean finite because this sum here, it will just run from 1 up to k. But this one here, it's this one, and this one here is your S sub k. So that's the definition of a convergent series or divergent series. So in the following slides, we will see several examples of series and some techniques on how to obtain the actual sum of a series if they exist and if our means is applicable. First, let us consider this one here. We want to find the sum of 1 over n times n plus 1 and running from 1 up to infinity if it is convergent, or otherwise explain why it is divergent. So look at this fraction here and try to recall how to do partial fractions when we did some integration. We can use a similar technique. Well, we actually use the same technique, partial fractions. We will try to decompose this, and maybe we can use the decomposition in order to find the actual sum of this series. So 1 over n times n plus 1. In our methods, we can rewrite this as a over n plus a over n plus 1. Oh, sorry, not a for the second one. Let us use capital B. And then we combine it again. You will have a times n plus 1 plus b times n over n plus 1 times n. Then we can find the actual values for a and b. For example, if we take n equals 0, we will have a times 0 plus 1 plus b times 0, and this should be equal to this numerator because, well, that is just constant 1. So this means that a is equal to 1. And if we choose n equals negative 1, we will have here a times negative 1 plus 1 plus b times negative 1. Again, that's equal to 1 because in here, this is just constant. But this means your b equals negative 1. Note that our n here starts from 1. But in here, we use n equals negative 1. It doesn't really matter. Whatever number you can use um, in order to find your b, it's allowed. I mean, this one is just a method of decomposing the fraction. So you can use any number. But when you are trying to add the terms, you actually start with n equals 1. Yeah, n equals 1. So anyway, what does this mean? We have your series sum 1 over n times n plus 1, and from 1 up to plus infinity, you can write this as 1 over n minus 1 over n plus 1, and from 1 up to plus infinity. From here, we can use our definition. We will define the sequence of partial sums. Let us write that. So what we have written in the previous slide, we have 1 over 1n plus 1 over n times n plus 1, and from 1 up to plus infinity, we can write this as the sum of 1 over n minus 1 over n plus 1, and from 1 up to infinity. Now, let us consider the sequence of partial sum. S1 will just be the first term. When n equals 1, you will have 1 minus 1 over 2. In here, you might be tempted to write this as 1 half, 1 minus 1 over 2. But I suggest we keep this form here. Now, what is S sub 2? S sub 2 will be, let us write it here, your A1 plus A2. So n equals 1, n equals 2 here. For n equals 1, we have here 1 minus 1 half plus n equals 2, you will have 1 over 2 minus 1 over 3. So 1 over 2 minus 1 over 3. And as you can see here, we can actually cancel this and this because there's a minus 1 half and then there's a plus 1 half here. If you want a sub 3, we will have here a sub 1. Let me write that again. A sub 1 plus a sub 2 plus a sub 3. For the first one, you will have 1 minus 1 half plus. For the second one, there is 1 half minus 1 third plus. For the third one, you have 1 third minus 1 fourth. So n equals 3. We added the term n equals 3. So this is 1 third minus 1 over 3 plus 1, which is 1 fourth. And you will observe again that this 1 minus 1 half will cancel this 1 half. This minus 1 third will cancel this plus 1 third. So essentially, if we simplify this, this is 1 minus 1 third. This is 1 minus 1 fourth. Let's have another. S sub 4. S sub 4, this is A1 plus A2 plus A3 plus A4, but this is the same as S sub 3 plus A4. S sub 3 is precisely these numbers here. And then you add the fourth term. We already know what S sub 3 is, so we can write that S sub 3 is 1 minus 1/4. The A4 will be, if you look at this, again, n equals 4, that will be 1/4 minus 1/5. And observe that this 1/4 here will cancel the 1/4 here. So that this will go to 1 minus 1 over 5. And try to observe what happened. S1, you got 1 minus 1/2. S2, you have 1 minus 1/3. S3, you got 1 minus 1/4. S4, you got 1 minus 1/5. And it seems that there is a nice pattern. If we continue, our S sub k will be equal to 1 minus 1 over k plus 1. Try to recognize the pattern. 1 here, this is 2. 2 here, this is 3. 3 here, this is 4. 4 here, this is 5. So if this is k, this will be k plus 1. So this forms the pattern for the sequence of partial sums, which means that if we try to get the limit of sk as k approaches infinity, this is precisely the limit as k approaches infinity of 1 minus 1 over k plus 1. And as k approaches infinity, this will go to, oops, not 0, but this will go to 0. Sorry, not infinity, but will go to 0. So the limit will be equal to 1. Therefore, we can conclude that this series here, sum of 1 over n times n plus 1, and running from 1 up to plus infinity, this is equal to 1. So we can conclude that this series here is convergent. Now, this type of series, if you can write it this way, we call this telescoping sum. Telescoping sum because, well, I explain it this way. I usually explain it this way, what telescoping sum is. You started with the first term or the first few terms, and then you are just getting the last few terms of your SK. For telescoping sum, you normally cancel some middle terms. Telescoping because when you look at the telescope, you look at the eyepiece, and then you see what's far ahead using your telescope. So it's like this is your eyepiece, and this is the object from very far away. So telescoping sum. That's a generic term for this type of series. Okay. Now, show that the harmonic series is divergent. The harmonic series is this form. You got 1 over n as the term of the series. So the harmonic series, it's the sum of 1 over n running from 1 up to infinity. So it is said that this series is divergent, or at the very least, this according to this problem, you want to show that it is divergent. So this is a popular series. So in here, we will show that this series is divergent. Well, we consider S case. So first S1, this is just 1. S2, this is just 1 plus 1 half. S3, this is 1 plus 1 half plus 1 third. S4, this is 1 plus 1 half plus 1 third plus 1 fourth, and so on and so forth. Let us write some more terms. S4, S5, S5, we will have 1 plus 1 half plus 1 third plus 1 fourth plus 1 over 5. And let us skip some s's. What I'm going to write is s sub 8. S sub 8, that's equal to 1 plus 1 half plus 1 third plus 1 fourth plus 1 over 6 plus 1 over 5 first. 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8. And we can do this to the next S that we will need, but I will show you the pattern. So for S1, we just have here 1. For S2, we have here 1 plus 1 half. Let us skip S3, and I will do S4. Particularly, if you look at this here, we know that 1 third is greater than 1 fourth. 1 third is greater than 1 fourth. And of course, you got here 1 fourth. So what we actually have in here is that S4 is greater than 1 plus 1 half plus 1 fourth plus 1 fourth. But 1 fourth plus 1 fourth is equal to 1 half. So 1 plus 1 half plus 1 half. Next, let us skip and go to S8. We already know that this one here is greater than 1 plus 1 half plus 1 fourth plus 1 fourth because, well, 1 third is greater than 1 fourth. And then what we're gonna do is to look at these terms. So we are going to look at these terms. Your 1/5 is greater than 1/8. 1 over 6 is greater than 1/8. 1 over 7 is greater than 1/8. So this S8 here is still greater than this thing here, this expression here, and again much greater if we replace 1 over 5 with 1 over 8. 1 over 6 replace it with 1 over 8. 1 over 7 replace it with 1 over 8. And of course 1 over 8, we retain it. Okay, so again, your 1 third, that's greater than 1 fourth. 1/5, 1/6, 1 over 7, they are all greater than 1 over 8. But if we simplify this now, this is equal to 1 plus 1 half plus 1 half plus 1 half. So this here is this 1 half. This here is actually this 1 half. You can continue with this pattern. The next S that you will consider is S sub 16. The terms next to this 1 over 8, the terms that you will get in here, each of them is greater than 1 over 16. But there will be 8 of them. Well, if I include 1 over 16 at the end, 1 over 16 there, and then from 1 over 9 to 1 over 15, each of them is greater than 1 over 16. But if you add all of those 1 over 16s, there are 8 of them, that's also equal to 1 half. So let us write that your 1 over 16, or S sub 16, this will be greater than 1 plus 1 half plus 1 half plus 1 half plus 1 half. This is from your S1. This is your S1. This is your S2. This one S4. This one S8. And this one S16. And then you can have your S sub 32. This is greater than 1 plus 1 half plus 1 half plus 1 half plus 1 half. And then there's another 1 half here. The pattern that you will recognize is S sub 2 to the k minus 1. Again, let us go back. This one here is S sub 2 to the 0. This one here is S sub 2 to the 1. This one here is S sub 2 squared. This one here is S sub 2 cube. This one here is S sub 2 to the 4th power. This one here is S sub 2 to the 5th power. Let us just write the subscript as S sub 2 to the k. But anyway, the pattern will be your S sub 2 to the k will be greater than 1 plus something. 2 to the 5, we got 1, 2, 3, 4, 5 1 halves. 2 to the 4, we got 1, 2, 3, 4 1 halves. So in here, S sub 2 to the k will be greater than 1 plus k over 2. Correct? So, what does this mean? The limit of 1 plus k over 2, k approaching plus infinity, this will be equal to the limit. This will be equal to, actually, that will be less than to the limit of S sub 2 to the k approaching infinity. But this here is equal to the sum of 1 over n from 1 up to plus infinity. By definition, this here will give us the equality. So the limit of s sub 2 to the k as k approaches infinity will be greater than the limit here. But the limit here actually is going to infinity. So it means infinity is less than the sum of 1 over n and from 1 up to plus infinity. I'll put this as quote unquote. So what does this mean? This one will not have a sum because it's still greater than this infinity. And this shows that the harmonic series 1 over n and from 1 up to infinity is divergent. So that's how we show that the series is divergent. Okay? Now, let's have another series here. We call them the geometric series. Geometric series, this is a series of this form. Sum a times r raised to n minus 1 and from 1 up to plus infinity. So if you explicitly write it, it's a plus ar squared plus ar cubed plus so on and so forth, where a and r are non-zero constants. Of course, if a is 0, then it's just um, adding zeros, right? If r is equal to 0, then you'll just have a because all of these will be 0 except for this one. So this series, I want you to know it by heart because it's a very important series. It's one of the best series that you will be using a lot of times. So we will summarize immediately the convergence or divergence of this series. The geometric series, which is given by this, is convergent if the absolute value of r is less than 1. And the actual sum can be calculated using this formula, a over 1 minus r. It is divergent if the absolute value of r is greater than or equal to r. As a homework, try to prove this theorem. Meaning, try to try to find out this formula or derive the formula. Now, there will be some other forms of this series. Sometimes we will write this as the series AR to the n, but your n is starting from 0. Take note, n equals 1, the exponent of r is n minus 1. So if the exponent is n, then the series must start from n equals 0. In the formula here, our n starts from 1. So if the series does not start from 1, this formula should be adjusted. Okay? Some example here, determine if the series converges. If it does, find the sum. Well, let us look at this. Our formula was the sum ar to the n minus 1 and from 1 up to plus infinity. If you look at this, this is already starting from n equals 1. So if the sum exists, it will be a over 1 minus r. If you look at this, pi is raised to n minus 1, your 3 is raised to n. But we can combine this expression into a single expression with the common power form. What I'm saying is we can write pi to the n minus 1 over 3 to the n, and from 1 up to plus infinity as sum here, pi to the n minus 1 over 3 to the n minus 1 times 3. And from 1 up to plus infinity. Or we can write this as the sum and from 1 up to plus infinity of 1/3 times pi over 3 raised to n minus 1. Now, pi is approximately 3.14. So pi over 3, this will be greater than 1. 3.14 divided by 3, that's greater than 1. So, this means that the series pi to the n minus 1 over 3 to the n and from 1 up to infinity, this one is divergent. Okay? So we don't have to find the sum because, well, the series is divergent. Next, determine if this series is convergent. If it does, find the sum. If you look at this, your k starts from 0. So we must have sum, say n equals 0 to plus infinity, and we have here a r to the n, not n minus 1, because we are starting from n equals 0. So we have to write this expression here as something times r to the power k. This one is to the power k, but this one is to the power k minus 1. So, well, the formula will be a over 1 minus r. Let us rewrite sum, negative 2 to the k over 3 to the k minus 1, k from 0 to plus infinity. You can rewrite this as the sum k from 0 to plus infinity of 3 times negative 2 to the k over 3 to the k. Of course, if you bring this down to the denominator, it will be 3 raised to negative 1. 3 to the k times 3 to the negative 1, it will give you 3 to the k minus 1. Furthermore, we can rewrite this as sum from k equals 0 to plus infinity of 3 times negative 2 over 3 to the power k. So this becomes our a, and this becomes our r. The absolute value of negative 2 over 3, this is 2 over 3, which is less than 1. So the series converges, this series here converges, and the sum will be equal to, so the sum, negative 2 to the power k, 3 to the k minus 1, k from 0 to plus infinity, this will be equal to what? A is equal to 3. The denominator will be 1 minus r, but our r is negative 2 over 3. So let us simplify this. We got 3 over 1 plus 2/3. This will be 3 over 1 plus 2/3, that's 5/3. So this will be 9 over 5. So the sum of this one here is 9 over 5. Okay? Now, some basic properties. If you have two infinite series that are convergent, you can add and subtract them. You can add and subtract them. And then you will be able to form the new series with terms an plus or minus bn. So you got two series here, sum of an, sum of bn. If they are both convergent, then you can form the sum an plus bn. And the actual sum here is just, well, adding or subtracting the actual sums for this one and this one. Basically, it tells us that if your series are convergent, you can distribute the summation symbol. If C is not equal to 0 and the series AN is convergent, then you can multiply each term of AN by that C. And your series, your new series, will still be convergent. The sum will be just sliding out the constant C outside. And get the sum of your AN, multiply that by your C. Similarly, if your series is divergent, then multiplying the C to the terms will give you a series that is also divergent. Now, for any positive k, if you got a series like this, sum from n equals 1 to plus infinity, and another series that looks like this, you start from k instead, ak plus ak plus 1 plus ak plus 2, etc., etc., then the two series will have the same convergence type or divergence type. They are both convergent or they are both divergent. So this means that even if you remove a few terms of your series, the series will still be convergent if the original series is convergent, or the series will be divergent if the original series is divergent. So removing few terms won't affect the convergence of your series. Definitely, if they are both convergent, they will have different sums because you have removed some terms from here, right? So if you remove some terms, the sum will be different. Now, one important theorem that we are going to use is called the divergence test. So in order to know this divergence test, we look at this particular theorem here. If you got a series that is convergent, then the limit of your an must go to 0. So if you got a series that is convergent, then the limit of the terms must go to 0. The tails must go to 0. So what is the divergence test? If you got a series, and you found out that the tails does not go to 0, then your series must be divergent. Okay? So again, you got a series, and you found out that the limit of your tails does not go to 0. Then your series must be divergent. Okay? So this is what we call the divergence test. This is a test for divergence. It is not a test for convergence. Okay? This theorem guarantees divergence of a series if the terms do not approach zero. However, if the limit of an is equal to zero, your series may or may not converge. Okay? Your series may or may not converge if the limit is equal to zero. For example, the harmonic series. The limit of an here, limit of 1 over n, as n approaches infinity, this equals 0. But the series 1 over n is divergent. Okay? This one, the limit of 1 over n times n plus 1, as n approaches infinity, this is also equal to 0. But the series, we already calculated this is actually equal to 1. And from 1 to plus infinity. So it does not mean that if the limit of the tails is equal to 0, there's no guarantee. You have to use a different method. Okay? Next example here. Determine if this series converges or diverges. Now, note, first we got 1 over 2 to the n minus 1, n from 1 up to plus infinity. If you look at this, this is actually 1 plus 1 half plus 1 fourth plus 1 over 8 plus etc. When n equals 1, you got 1 over 2 to the 0, so that's equal to 1. When n equals 2, you got 1 over 2 to the 2 minus 1, that's 1 half. N equals 3, 1 over 2 to the 4, so that's 1 fourth, and so on and so forth. This is actually a geometric series. You can rewrite this as 1 over 1 half to the power n minus 1, and from 1 up to plus infinity. And as a geometric series, your a, that's equal to 1, and this is your r, and in fact, the absolute value of r is less than 1. So if we use the formula, this is what? 1 over 1 minus 1 half, this is equal to 2. For the other one, we got sum of 2 over n times n plus 1, and from 1 up to plus infinity, we can bring out the 2. This is 2 times the series 1 over n times n plus 1, and from 1 up to plus infinity, but we have already the answer for this part here. From a previous example, that's just equal to 1. So you will have 2 times 1, which is equal to 2. Both series are convergent. We are just adding the two terms of these two series. So we can find the sum of these two series. Therefore, sum of 1 over 2 to the n minus 1 plus 2 over n times n plus 1, and from 1 up to plus infinity, this is convergent. We are not actually required to find the sum. It only asks us if the series is convergent or divergent. But based on our calculations, we can actually write it, and is equal to 4. 2 from this and 2 from this. Last example here, determine if the series is convergent or divergent. For this one, what we're gonna do is to look at the terms. A sub n, it's e to the n over n squared. So if we look at the limit, as n approaches infinity of your a sub n, you can actually use, well, L'Hopital's rule when these terms are converted into functions. E to the x over x squared. So this is infinity over infinity by L'Hopital's rule. This is limit as x approaches infinity. This is e to the x, this is 2x. And again, infinity over infinity, we can apply L'Hopital's rules again. Limit as x approaches infinity, e to the x over 2, but this is equal to plus infinity. As a conclusion, well, the series e to the n over n squared, and from 1 up to plus infinity, this one is divergent. Let me just clarify this one here. This is n. Why? Because, well, the limit is going to plus infinity, which is not equal to 0 by divergence test. By divergence test. Okay? So, that ends the lecture for this set of videos or set of video. I'll see you in our next meeting.